Modern science explains the origin of the universe with the Big Bang theory. According to this theory, our world emerged from the explosion of singularity, a point in space-time where energy density and mass approach infinity, and all dimensions reach zero. But recently, Brian Cox has made a bold announcement stating that the universe has always existed, and the Big Bang theory is wrong. Big Bang theory presents the concept of singularity, where there was no time, space, or matter. But the question is, where did this singularity come from? What preceded it, and what triggered the countdown to the Big Bang? Has the universe always existed, or did it have a beginning?
The question for a scientist, particularly for physicists and biologists who are interested in the fundamentals of life, is how was it? How did it come to be that Earth is populated by so many wonderfully diverse organisms? And from a physicist's perspective, you want to go back all the way to the beginning. So this is a picture of the origin and evolution of the universe as we know it now. Now, we made a spectacularly precise measurement of the age of the universe quite recently, actually. The current number is 13.75 billion years old. So the picture is that 13.75 billion years ago, the universe began. Why? We don't know. We don't know the answer to questions such as what happened before the Big Bang. I get asked that a lot. The answer is we don't know. It's out there. It's current research. But we do know that the universe was extremely hot and extremely dense and extremely small 13.75 billion years ago. In fact, everything we can see in the universe today, we think at some point was compressed into something, and in fact probably smaller than an atom. So it's a tremendous thought. But what we know is the universe expanded and cooled ever since. And as it cooled, complex things began to, well, initially crystallize out. But it's a strange thought that we know fairly well at the moment, is just how precisely we understand how things began to crystallize out. And just from that ball of energy, 13.75 billion years ago, we get today things like DNA and planets and stars and people. How do you go about finding out? One way is to look up at the stars. The other way is to build machines that can explore the universe by recreating the conditions that were present close to the Big Bang.
Around 1600 years ago, St. Augustine, the theologian, sought to comprehend God's nature before the universe's creation and concluded that time was part of God's creation, and there was no before. In the 20th century, Einstein reached similar conclusions with his theory of relativity, which linked mass and time. Einstein demonstrated that time passes slower near massive bodies. For instance, our planet's enormous mass distorts time, causing it to flow more slowly for someone on its surface than an astronaut in orbit. While the difference is imperceptible, it exists. American scientists Robert Pound and Glenn Rebka demonstrated through an experiment that a clock on Earth's surface runs slower than a clock raised to a height of 22.5 meters. This precisely matched the theory of relativity's prediction. Remarkably, spending 1 billion years in a high-rise building would only make a person 1 second younger. The singularity preceding the Big Bang possessed all the mass in the universe, completely halting time. Consequently, Einstein's perspective suggests that discussing what occurred before the Big Bang is meaningless, as there was no before. However, this conclusion challenges the fundamental concept of cause and effect relationships in physics. Every effect must have a cause or a reason. For example, parents cause the birth of their children. Every human experience is tied to cause and effect relationships. Thus, Einstein's notion that nothing existed before the cosmic singularity feels counterintuitive, since it implies that the concept of the past cannot be a part of it. Could St. Augustine and Einstein have been mistaken? Is it possible that the cosmic singularity was not the beginning of everything? Nevertheless, scientists generally maintain confidence in the Big Bang theory.
The standard answer, as best we know at the moment, is that it doesn't expand into anything because it's space itself, and actually space-time, if you talk up to Einstein, that's expanding. So it's not the right picture to think of a Big Bang in a pre-existing space. It's not like that at all. It seems that, as far as we know, space and time began at the Big Bang, and they've been stretching ever since. And so a kind of a related idea is, where did the Big Bang happen? You think, well, we're in this big box of a universe. Did it happen over there or over there or over there? It happened everywhere, because all the space was made, as far as we know, at the Big Bang. So the Big Bang happened everywhere. So it's not expanding into anything. It's very difficult to picture that. What I should say is that the theory that deals with this, the underpinning, it's called Einstein's theory of general relativity. He wrote it down in 1915, and it's still our best theory of space and time, and the theory upon which all these interesting and strange ideas rest.
The theory is supported by factual evidence, such as the universe's expansion discovered by American astronomer Hubble in 1929. Additionally, the cosmic microwave background radiation evenly filling the universe, discovered by American scientists Penzias and Wilson in 1965, reinforces the theory. This radiation appeared 379,000 years after the Big Bang during the era of hydrogen recombination. The Big Bang theory proposes that in the first second of its birth, our universe was no larger than an atom, but managed to survive through 6 epochs. The Planck epoch spanned from the beginning of time to 10 to the minus 43 seconds. The Grand Unification epoch persisted until 10 to the minus 35 of a second, during which gravity separated from other fundamental interactions. Subsequently, the inflationary epoch extended up to 10 to the minus 32 seconds, causing the universe's volume to increase by a factor of 10 to 78. Next came the electroweak epoch, continuing up to 10 to the minus 12 of a second. It was during this epoch that quarks, leptons, photons, W and Z bosons, and Higgs bosons formed. The quark epoch followed, during which gravitation, electromagnetism, and the strong and weak interactions assumed their present forms. Finally, the Hadron epoch ensued, ending 1 second after the countdown, and the universe reached the size of an atom. At this scale, quantum theory governs classical physics. Cosmologists, including Stephen Hawking, began to ponder if quantum theory, used to describe subatomic phenomena, could be applied to the entire universe as a whole. This led to the birth of inflationary quantum cosmology. The astrophysicist John Gribben described inflationary quantum cosmology as the most significant advance in science since the time of Isaac Newton. This theory provides a way to address the singularity problem and the notion of nothingness before it. Classical cosmologists believed the cosmic singularity was akin to a point with zero volume. However, quantum theory introduced an essential element of uncertainty at the most fundamental level of nature. Consequently, it's impossible to pinpoint the precise moment of the universe's creation, its initial time or volume. An intriguing aspect of quantum theory is its allowance for the spontaneous emergence of particles from the vacuum. Quantum cosmologists wondered if the universe itself arose from a random fluctuation following the principles of quantum mechanics. If so, the reason for the existence of something lies in the instability of the vacuum. In physics, a vacuum refers to a state without particles, but it is not entirely empty. Heisenberg's uncertainty principle is a fundamental principle in quantum mechanics. According to the principle, certain pairs of properties are related in such a way that they cannot be accurately measured simultaneously. For example, the position and momentum of a particle constitute such a pair. The more precisely the position is known, the less precisely the momentum can be measured, and vice versa. Another such pair is time and energy. The more accurately the time of an event is known, the less precise the energy associated with the event can be measured, and vice versa. The concept of a perfect vacuum as a state where all field values remain constantly at zero is challenged by the Heisenberg uncertainty principle. According to the principle, if the value of a field is known precisely, its rate of change becomes entirely random, preventing it from being zero at all times. Thus, an unchanging emptiness described mathematically is incompatible with quantum mechanics. In simpler terms, pure emptiness is unstable, and true emptiness does not exist. It seems incredible that a universe consisting of billions of galaxies could emerge from the void. All mass represents a condensed form of energy, united through Einstein's famous formula, energy equals mass times the speed of light squared. However, the vast positive energy bound in stars and galaxies must be offset by an equal amount of negative energy from their gravitational pull. In a closed universe with a finite lifetime that will eventually contract again, positive and negative energies must balance each other. This results in the total energy of such a universe being zero. Stephen Hawking pondered how the universe could be created from nothing if its total energy remains zero, as creating a body requires expanding energy. This leads to the necessity of gravity, which has negative energy due to its attractive nature. To separate a gravitationally bound system like the Earth and the Moon, work must be done. This negative energy can be offset by the positive energy needed to create matter. However, the situation is more complex. A star, for example, has more negative gravitational energy, and the smaller it is, the greater its negative gravitational energy becomes, before the negative gravitational energy exceeds the positive energy of matter. A star collapses or shrinks into a black hole. A black hole, in turn, has positive energy. As a result, empty space remains stable. Objects like stars or black holes cannot simply appear out of thin air, but the entire universe can. Quantum mechanics also aligns with Stephen Hawking's conclusions. Alexander Vilenkin, an American scientist, demonstrated that a tiny piece of vacuum filled with energy can spontaneously emerge from a state of emptiness. Under the influence of negative pressure from cosmic inflation, this piece of energetic vacuum expands rapidly. Within microseconds, it reaches cosmic dimensions, emitting light and matter, eventually creating the Big Bang. So an ingenious explanation emerges. The universe came from nothing. There was nothing before, no energy, no space, and no time. This nothingness was sustainable, and questioning how long it existed is irrelevant since time did not exist during this era of nothing. The world arose from a random quantum fluctuation of the void. So, is the most profound question resolved? Or perhaps a more significant question would be whether this quantum fluctuation was truly random. As Einstein once said, God doesn't play dice. With that in mind, what implications does this have, and what prevents another tiny piece of vacuum filled with energy from reappearing, leading to a new Big Bang with a 100% probability of erasing humanity? In the realm of physics, there are fundamental constants that, when combined, derive all physical laws. These constants include the speed of light, the gravitational constant, Planck's constant, the masses of the electron and proton, and the charge of the electron. Physicists noticed that even the slightest deviation in any of these constants would prevent the existence of our universe. For instance, altering the speed of light from 299,792,458 meters per second to 290 million meters per second would have catastrophic consequences on the stability of atoms and stars. The fine-tuning of these constants is a puzzling problem. Another intriguing question is why our universe is three-dimensional, despite Minkowski's space having 4 dimensions in the geometric interpretation of the special theory of relativity.
Imagine that we're not in this three-dimensional space. Just forget one of the dimensions. So imagine we're on a sheet. So imagine we lived on the surface of a sheet of paper. And imagine the forces of nature, particularly light, travelled on the sheet. And then there's another force called the nuclear force, the strong nuclear force that sticks your atomic nuclei together. Imagine that only works on the sheet as well. And imagine there's another force called the weak nuclear force. Imagine that only works on the sheet. Then what would happen if there were another sheet, another universe, if you like, just floating a millimetre away, let's say? Well, you wouldn't see it because light is confined to your sheet. You wouldn't feel it because the forces don't come off the sheet there. So it could be there. Now, if that's true, then we can try and do experiments and say, how would we possibly detect it? Not really well known, but there are some signatures of these extra dimensions, as they were, that you can see at the Large Hadron Collider at CERN. It's very speculative stuff. So it could be, I find this remarkable, that there's another universe a millimetre away from your head in a big sheet stretching out infinity in all directions, and you just don't perceive it because the forces that are exerted on us that hold us together don't travel from one sheet to the next.
Paul Ehrenfest's discovery revealed that the orbits of planets lose stability in 4 or more spatial dimensions, leading to the impossibility of our universe's existence in such conditions. In light of these observations, scientists proposed the anthropic principle. Posits that observers have the potential not only to influence the universe, but also to impact the laws governing it. There are 2 versions of the anthropic principle, the weak and the strong. The weak anthropic principle asserts that we observe a universe with a structure suitable for the emergence and development of life. On the other hand, the strong anthropic principle posits that the universe must have properties that allow intelligent life to evolve. A variation of the strong anthropic principle is the participatory anthropic principle, which suggests that no phenomenon exists until it is observed. This principle posits that observers may be essential to give meaning to our universe, but there are alternative ideas within the scientific community. The theory of cosmological natural selection, or second universes, is an ongoing discussion. According to this theory, each black hole in our universe gives rise to a new universe on its other side. In these universes, the fundamental physical constants may differ from those in the universe containing the corresponding black hole. Intelligent observers can emerge in universes where these constants favor the development of life. This process resembles mutation and selection in biological evolution. Some scientists consider this model a more suitable explanation for the fine-tuning of the universe. In the theory of second universes, life emerges through natural selection, where universes with the right parameters for more black holes would have more descendants, increasing the probability of life's presence there. Recently, on a BBC series, Universe, where everything begins and ends, the renowned physicist Brian Cox delved into the fundamental question: how did the universe come to be? Cox explained the Big Bang theory. However, he challenged the conventional understanding by introducing a fascinating perspective. He strongly suspected the existence of a time before the Big Bang. This intriguing idea opens up a new dimension in our understanding of the universe's origins. Cox's concept of the pre-Big Bang universe connects to the theory of cosmic inflation. According to this theory, the universe experienced an exponential expansion during an infinitesimally short period shortly after the Big Bang. This dramatic growth allowed the universe to become remarkably smooth and uniform, providing an explanation for its observed homogeneity at large scales. While inflation remains an integral part of the prevailing cosmological model, Cox's idea of a pre-Big Bang state adds an extra layer of complexity to the timeline of the universe's evolution. The question arises, what could have caused this primordial energy to trigger such rapid expansion? Could it be the result of interactions between forces that have yet to be fully understood? Cox's ideas on time before the Big Bang find support from the work of Sir Roger Penrose, a distinguished mathematician and physicist who was awarded the Nobel Prize for Physics for his pioneering contributions to our understanding of black holes. Penrose's work not only focuses on black holes, but also explains the early universe. Penrose proposes the concept of eons, a succession of cosmic epochs that occur within a cyclical framework. According to his theory, each eon begins with the Big Bang, followed by an era of expansion-contraction and culminating in a big crunch, where the universe collapses back to its original state. This cyclic process sets the stage for a new eon, and the cycle continues indefinitely. Central to Penrose's eon theory are black holes, celestial objects of immense gravitational force that result from the collapse of massive stars. As black holes evaporate over immense timescales through Hawking radiation, they release energy, ultimately leading to their disappearance. Penrose speculated that dead black holes from previous eons might still exist today, potentially leaving imprints on our current observable universe. These remnants, which Penrose termed Hawking points in honor of the late physicist Stephen Hawking, could serve as evidence of the existence of pre-Big Bang states. Penrose's proposal of Hawking points represents potential observational evidence for the existence of the pre-Big Bang universe. These enigmatic points, roughly 8 times the diameter of the Moon, are slightly warmer regions in the sky, detectable through advanced observational techniques. While the concept of Hawking points awaits further validation, Its presence in the scientific discourse highlights the fluidity of our understanding of the universe's beginnings. The debate around Hawking's points and their interpretation underscores the importance of continued scientific exploration and the potential for paradigm-shifting discoveries in the future. As with any revolutionary scientific proposal, Brian Cox's and Roger Penrose's theories on a time before the Big Bang face challenges and controversies. Critics argue that the concept of a pre-Big Bang universe remains speculative, lacking direct observational evidence. Additionally, the cyclical nature of Penrose's eon theory raises questions about the conservation of energy and the universe's ultimate fate. Some skeptics question the feasibility of an infinite cycle of eons, as it might seem to contradict the laws of thermodynamics and other fundamental principles of physics. Now let's explore another related theory in cosmology, the multiverse hypothesis. The multiverse hypothesis is a concept that suggests the existence of multiple universes, each with its own set of physical laws, constants, and properties. This idea is rooted in the belief that our universe might be just one of many in a vast and diverse multiverse. The concept of the multiverse has gained traction as a way to explain certain aspects of our universe that appear finely tuned for life. Scientists have observed that the fundamental constants and physical laws governing our universe seem to be precisely balanced to allow for the emergence of life as we know it. This observation has led some to propose the anthropic principle, which posits that our universe appears the way it does because it must support the existence of intelligent observers like us. However, the notion of a finely tuned universe raises the question of whether it's just an incredibly fortunate coincidence or if there's a deeper explanation. The multiverse hypothesis proposes that our universe is just one of countless others, each with different physical parameters. In this vast array of universes, the finely tuned ones would naturally arise, and we find ourselves in one of them simply because we couldn't exist in any other. One prominent version of the multiverse theory is the inflationary multiverse. According to this idea, the universe underwent a rapid expansion phase known as cosmic inflation shortly after the Big Bang. During this inflationary epoch, different regions of space could have expanded at varying rates, leading to the formation of distinct bubble universes. Each bubble universe would have its own unique set of physical laws and constants. While the multiverse hypothesis is intriguing and addresses the fine-tuning question, it also faces significant challenges. One major hurdle is the lack of direct empirical evidence for other universes beyond our own, since these proposed universes are causally disconnected. It's incredibly challenging to test or observe them directly. Critics of the multiverse theory argue that it lacks empirical verification and falls into the realm of untestable speculation, making it more of a philosophical idea than a scientific theory. They argue that the explanatory power of the multiverse is limited since it doesn't offer testable predictions that can be validated through observations or experiments. Despite the challenges, some physicists and cosmologists find the multiverse hypothesis compelling due to its potential to address certain cosmological puzzles. For instance, the concept of eternal inflation, where new universes constantly arise through inflationary processes, could provide an explanation for the vastness of our cosmos. Others see the multiverse as a way to understand the fundamental nature of reality and the existence of multiple possible outcomes in the quantum realm. In quantum mechanics, particles can exist in multiple states simultaneously until observed, which raises the question of whether all possible outcomes exist simultaneously in parallel universes. The multiverse hypothesis has also found connections with string theory, a theoretical framework in physics that posits the existence of higher dimensions beyond the familiar 4 dimensions of spacetime. Some versions of string theory propose the existence of a landscape of possible vacuum states, each corresponding to a different universe with unique physical properties. While the multiverse remains a subject of ongoing debate and investigation, it serves as an essential thought experiment in cosmology. Exploring the concept challenges our understanding of the universe and encourages scientists to seek ways to probe the boundaries of our knowledge further.